Okay, welcome back. So we're really going to enjoy this, I can tell you. This is going to be some real fun maths. Okay, so what are we going to be given? We're going to be given a circle. I'll just hand sketch it here. Let's start down here. We're going to be given a circle. We know its center, and we're going to have 2 points on it. Okay, so we're going to be given this circle, and we're going to be showing that this angle here that I'm indicating is double this angle up here. Now I can take any random point here. It can be offset a bit to the left or whatever, and like this. Okay, now I'm going to just blow that up because we're going to be looking at isosceles triangles and everything. Okay, so what I'd normally say to you when we're constructing this in class is stay a little bit offset so you don't think there's too much symmetry there, but at the same time this can end up cutting in here and it's nicer this way. Okay, so they're equal because it's an isosceles triangle, and that's important. And we're also going to construct this line from there to there. We're going to extend it out here. Okay, which makes that also equal to this, which is equal to this, because they're all radii. Now, because this is an isosceles triangle over here, I can say that those two angles are equal. And either by the external angle theorem or a few other methods, I can say that this is double that. But let's make it the external angle. So the external angle is double the sum of the two internal angles. And very similarly, just going to use dots again, but red dots, those two angles which are different have to be equal to these two angles using, so what have I done? I've used isosceles. I've used two isosceles triangles, and I've used the external angle theorem to give myself that this angle here is 2 reds and 2 blacks, and this angle here is 1 red and 1 black angle. Okay, so I've proven it. What were my constructions? I've drew in a few lines, and because you only have to understand the proof, you don't have to produce it, they might show it to you and ask you, or they probably just ask you, what do you use? And you will say you use isosceles triangles and external angle. So if you follow that, you've done all the work. The time's gone by, you used to have to learn off the proof and might be asked to produce it in the exam. You won't be asked that anymore. Okay, what really matters is when you're given something like this, and you're told this is 80 and asked for this, you tell me that you have to write down that that's 40 based on this circle theorem, and vice versa. So we move on to theorem 6. Well, this is a very easy one. Okay, so you just extend the base of a triangle and you put it up there like that. So this is a generic triangle with angles A, B, and C. And you extend along the vertex, you create this parallel to this. Okay, which makes this, no, I got that wrong. Which makes this angle A because they're alternate. Why? Because these are parallel, so this is a transversal. And so these are both A. And this is a different transversal with a C here and a C here. So there you have it. You have a straight angle. You have a straight angle 180 degrees, and a straight angle is A plus B plus C. Okay. But the internals add up to 180 as well. So hold on now, what am I trying to do here? Actually, that was the internals. What about this? Well, actually, here's my straight angle. This is where I use this. So here's my straight angle. Let's just call this angle D. So I have C plus D equals A plus B plus C, because they're both 180. And then you can cross out the C's, eliminate the C's of both sides, and that's it. D is equal to A plus B. Let's do the whole thing again, fresh and cleaner. And remember, you just need to see this once, understand it once, And that's it, because that's all the syllabus asks you to do. So we go again. You start off with a generic triangle with angles A, B, and C. You extend this out so you can create this external angle, which we will call D. Okay? We have to show, to prove, that angle D is equal to angle B plus angle A. That's what we have to prove. What is the proof? Okay, so your construction. Hold on, I'm thinking, you know what? I didn't need to do that. I confused that with a different theorem. I didn't need that line up there. So the theorem is that A plus B plus CD internals add to 180. C plus D is 180 first because it's a straight line. So that's triangle angles. C plus D is a straight angle. And then we can go 180 minus C in both cases. So 180 minus C. So A and B is 180 minus C. And D is 180 minus C. And because both of them are equal to themselves, then these two are equal. And you rest your case. You're finished. A plus B equals D. Now, some little point here. I can do that and be a bit lazy about saying it. What I mean is the size of angle A plus the size of angle B equals the size of angle D, because the junior cert just lets you refer to the angles like A and the size of the angles as if it's more in the same thing. So don't worry about that, and you're done. That's that theorem done. Now, in a parallelogram, opposite sides are equal and opposite angles are equal. So what we will say is we know that these are parallel. We will draw in two diagonals. Opposite sides are equal. Then we will show, and it doesn't take long, this top one is congruent to this bottom one. It won't take long at all to do that. And once we've done that, because of the congruency, then corresponding sides are equal. And the congruency will also give us that opposite angles are equal. You know, I think we might only take this one diagonal, and then we'll be able to show that these two angles correspond, which will give us that second bit, opposite angles. Okay, so our construction is the diagonal. We're proving that length AC equals length DC, and that the angle at A is equal to the angle at C. It's quite obvious, so I'm just going to use the single letter. And that's what we're proving. We've done our construction. Here comes the proof. Okay, so we'll say you can't start off with the top angle is congruent to the bottom angle. We have to build it up through. We know these are parallel, so we say that's equal to that, because alternates. So CDB is congruent to DBA. Just take your time with that and go around, you know, trace it out from corner to corner to corner. There's no easy way of doing it, but they're equal because they're alternates. And it's given, by the way, it's given to you by definition that these are parallel. So I've done angle. This side is common. I'm going to need another angle, which will be this one here, will be a different angle down here. But that is congruent to this. The reason I need another angle is I can't use a side length because I'm trying to prove a side length. So I have to use angle side angle. I've got my blue angle and I've got this common side, which is really important, so I'm going to say it. DB is equal to BD because it's common. Okay, and now I've proven angle side angle congruency, so I'll use the names of the triangles. I'll say, hey, by the way, now I know that triangle from A, I need to start, where's my angle? Angle, side angle. Yeah, I just go A, B, D, the top one, is congruent. I have to go through this in the same order. So when I came along that way into the red dot, I'm going to go this way into the red dot as well. So CDB as a triangle. Okay, so CD, what did I say? CDB. They're congruent because I've just shown that it's angle, side angle. And then once they're congruent, corresponding sides and corresponding angles have to match, which they do, and then you can say that's equal to that, you can say that's angles equal to that angle. Done. Next, trying to give it to me, sure I can give it myself. Theorem. No. Yeah, that's a nice proof, I like it. Let's go with this. Don't want to see any of this, do I want, because it's not really original, it's very slow. So let me show you the theorem. So there's your construction. We'll just go back to it. Give it a minute. Yeah, nice construction. So to prove that, again. So page 16, you have this triangle ABC with a right angle here, and you're proving this: c squared equals b squared plus a squared. And the way we do it is, as you can see here, we're putting in this perpendicular, and it creates these similar triangles. Now, similar, not equal. And that, I'll show you now why they're similar. Prove the circle one later on, yeah. Okay, I'll show you why they're similar. Well, 3 and 4, the way they've done it there, is definitely a right angle. But 2 and 4 is 90 degrees as well, which means 2 and 3 are the same thing. 2 is up here. Okay, so I can scratch 3 and put in a 2 here, same as that one. Okay, and similarly, well, 1 is enough. So knowing that those two angles are equal means that this angle down here is 4. Okay, that these two are equal. So let's just replace that visually by putting in a red dot here, and a red dot here, and a blue dot here, and a blue dot here. Okay? So now we have similarity between these two triangles. And so I'll go opposite my red dot is AD on the left hand side, and then opposite my blue dot is from D to B. So I'll say that that triangle is similar. Again, opposite my red dot is CD along here, and then I'm going up that way opposite my blue dot, which I'm already at D, and going on up to A. So they're congruent. I meant to put a triangle symbol here. And if they're congruent, then we can say AD divided by CD. I think is an extra little thing I need to do now in a second. I'll be adding these two together in a second. No, I won't. See. I can also do this congruency here. Look, that's red. That's red. I don't want to use the two small ones. I want to, and that's blue and that's blue. Okay, I want to say this big one here is congruent to this one, and it's congruent to this one, and this big length will be equal to those two lengths together. Okay, I just say I've probably done enough. I'm going to skip past it because I just know it's so, the proof is so unimportant. We'll follow it in the book in class. Look, they've more or less done it all there, but adding yeah, the big one and a small one on the right. Now consider this. Yeah, it sounds fine. I'm sure I can do it, but I want to drive on because I want to get to the end of it, which is 19 now. Sure, I proved 19 already somewhere else, didn't I? So, oh, the angle of the center standing on a given arc is twice. Yeah, no, I proved that earlier. I proved that up top. Proved that here. The angle of any. Oh, I did the wrong proof in the wrong place. So that was a proof for the end. And I'll just prove this one real quick if I didn't do it already. You extend your base straight out. You do a parallel line to it through the vertex. And I've kind of shown you this. You can start anywhere. You can go A, B, C. And this is B because they are not transversals, they're alternates. And if this is A because they're alternates, then that's equal to 180. So the three of them are 180. That's that proof. And then you can take that one that I did here with the isosceles and external and take it out to the end. And that's it. There's no questions here. Okay, as always,